All right, hello and welcome, guys. We're just going to go through some of the solutions for the question, I guess some of the trickier questions, the questions that students have asked help for. All right, so this question wasn't specifically asked for, but I definitely want to go through it just because I noticed there were some students making mistakes with it. It is question 3 from the multiple choice. By the way, this video, just so that you know, is just going to be on the multiple choice questions, just because I was doing it before and the video was getting too long. And I know historically, if there's a video that's too long, people generally won't click on it. They'll just sort of ignore it. So I'm breaking it up into a couple different smaller videos, which will hopefully help people click on, watch, and learn. Okay, so this first question, we're trying to find which of the following is equivalent to this expression here. It almost looks like the double angle result for tan, just they've got a plus there instead of a minus. It might be very tempting just to assume that they made a mistake and put down the answer C. But in this case, your initial assumption should at least be there isn't a mistake and it's actually going to be one of the others. And that's actually what ends up being the case here. So let's have a quick look. What do we have? We've got 2 tan theta all over 1 plus tan squared theta. Now, I'm just going to leave that there for the moment. I'm just going to deal with the 1 plus tan squared. That is as a result from the mathematics course, right? One of the 3 Pythagorean identities, and it is sec squared theta. If you forgot that, you need to go back to the advanced trig course. Make sure you look through the trig identities section. It's like the funnest part of prelim. You definitely don't want to miss it, and you definitely want to know how to do it. From this point, tan is, of course, sine over cos. We're dividing by sec, which is sec itself is 1 over cos. Well, sec squared would be 1 over cos squared. You're dividing by it. So ultimately you end up timesing by cos squared theta over 1. Again, I'm just, replacing sec with 1 over cos and then dividing the fractions just like I would in year 7. And of course, coses will cancel, giving us 2 sine theta cos theta, which funnily enough actually ends up being the double angle result for sine. So the correct answer is B. And I'll be honest, I didn't even know this myself, but there it is. If you replace a double angle result for tan, if you replace that minus with a plus, it actually is just another fancy way of writing the double angle result for sine. So pretty cool result. Anyway, so that should have been the answer for the first one. Question 5, which of the following is equivalent to this? It's a little bit blurry and a little bit hard to see here. So I'm just going to rewrite it a little bit better. This is actually a n plus 2 combination k plus 1. And this is an n plus 1 c k plus 1. So this is the expression we have been given. And we need to work out which one of these is equivalent to it. So let's start off. Look, there may be other quicker ways, but certainly the most direct way, the way they'll always work, is going to be replace these things with factorial notation, simplify it down, and see which one it is. So first step, replace these combinations with their factorial notation. And again, I'm just going to quickly go through and do it here. So this would be n plus 2 minus k minus 1. In other words, giving me this. If you have forgotten how to convert your combinations into factorial notation, you need to go back to the combinations, permutations and combinations topic, or combinatorics, whatever the textbook called it, and look back through that. But anyway, I'm just going to assume that you know how to do it at this point because we have already covered it. Okay, so convert it into factorial notation, you get this. And here we're just subtracting 2 fractions that have almost the same denominator. The only difference here being is The fraction on the left, one of the factors has a slightly higher term. Just to show what I'm talking about here, if you had the n plus 1 factorial is obviously the same, but if you look at n minus k factorial, that is all the numbers being times together right up to n minus k. However, you look at the one on the left, it's n minus k, but it also has this extra plus 1 in it. In other words, it's one number higher. It also is the multiplication of all of these numbers, but it goes up to the next number as well. It includes that extra number. So the only difference between the denominators is this one extra factor here. So what are we going to do? We're going to times top and bottom by the missing factor. That then now gives us our common denominator of n plus 1 minus k factorial all over k plus 1 factorial. And on the top, you'd end up having, well, I'm going to factorize out a n plus 1 factorial, leaving us with an n plus 2 from the first fraction. Take away, we're subtracting everything from the right-hand side, which ends up being a minus n, a take away 1, and we've got to take away a negative k, so I'm going to put a positive k there. Okay, so we end up with, I've got a chance of fitting this in actually. I'm going to get rid of this. Okay, so this is what we have so far. N plus 1 factorial. Over here, n's cancel. We've got a k, and we end up with a 2 take away 1. We've got a k plus 1 there. Okay. Now, okay, all right. Obviously, I was a little too optimistic. I'm not going to fit this on what's left of this page, although we are almost finished with the question. Current template. Okay, so if we go back to where we're at, let me just write it out again. So we have this, on the bottom we've got the n plus 1 minus k factorial all over k plus 1 factorial. What other simplifying can we do? We can see we've got this k plus 1's top and bottom. On the top we just had a k plus 1 term. On the bottom we had k plus 1 factorial, which, remember, is all the numbers being times right up to, you know, and including the k plus 1 term. And so here we can see we can cancel the k plus 1's, right? That k plus 1 cancels, leaving us left over with what would be k factorial, right? So once you cancel the k plus 1's, from the k plus 1 factorial, what you're left over with would just be k factorial. So we end up with n plus 1 factorial all over n plus 1 minus k factorial times k factorial. This, of course, is just n plus 1 c k, which if we go back, see, it was answer C. So that was question 5. All right, question 7. What is the exact value of cos 15? We don't know the exact value of cos 15, but we do know the exact values of 45 and 30. So we're going to use those ones there. So we're going to rewrite 15 degrees as 45 degrees, take away 30 degrees. And from here, we'll use our difference result for cos. So it'll be cos 45, cos 30, plus sine 45, sine 30. And now we can use our exact values. 1 on root 2 times root 3 over 2 plus 1 on root 2 times a half. And of course, here we are back in year 7, multiplying fractions. and then we can stay in year 7 for a little bit longer while we add fractions with a common denominator. That's the answer there. Now, if you actually look at the solutions that were given, which are not included here, none of the solutions were this, right? You'll notice that all of the solutions they give, all the denominator's been rationalized in all of them. So we're just stuck with the simple step of now just rationalizing the denominator. So in this case, how are we going to do that? Obviously, we're going to get rid of this root 2. We're going to times top and bottom by root 2. And doing that ends up giving us a root 2 plus root 6 on top, and a 2 times, well, yeah, root 2 squared ends up giving you this, which actually, I don't remember which letter it is, but this is one of the solutions that was given for question 7. All right, so they're the 3 multiple choice questions. Hopefully this helped for those that were having trouble with it. The next video we'll move on and we'll look at some of the harder questions in the written part. All right, thanks for that. Bye.